Hey, hi everyone, my name is Andrei, and today I'm going to be talking about our work overbooking in priorities respecting reassignment. This is joint work with Itai Ashlagi, Irene, who's in the audience, and the Mentzer. They're all from Stanford. So let's look at the following task of student assignment. Let's say that we have some students and some schools, 4 students and 4 schools, and let's assume that the students are ranked they're part of some ranking. So maybe you can think that maybe they're ranked by test scores, or by lotteries, or some combination of those, or other things. And let's also assume that the schools are ranked in the same way by every student. So you can think that maybe all the students agree on which one is the most popular school, the second most popular school, and so on. And let's also assume for simplicity for this example that the capacity at school is equal to 1. So we want to match one student to one school. So what would be the most common thing to do in this situation? Well, basically you would match the quote-unquote best student with the best school, the second best student, the second best school, and so on, expecting those rankings. So you would want this matching to be efficient and in some sense fair, and in some sense respecting those rankings of the schools and the students. Now, what happens in practice at the public school systems, and also for private schools, but most important public school systems, is that there's this opt-out stage. There's this period of time in which students can decide to forego their school assignment to opt for a different option. So in the public school setting, you can think that maybe the student at the top school found actually a private school that they like more, and they decided to go there. Now, for modeling purposes, we assume that this process is in some sense stochastic, so you can't really predict if you're a central plan trying to assign people to schools, you can't really predict what's going to happen. So yeah, you can assume that each person makes up their mind with some probability. There's some randomness associated with this situation. And so, because you want to reassign students, you don't really want to waste this AC at the most popular school. What you will have to do is that most likely you will want to move the student at the second school to the student at the first school to fill in that seat, a variable seat. Now, what that will do is that will cause the school 2 to have no student. So because you want to, in some sense, to preserve efficiency, you would have to move the student who was assigned to school 3 to school 2. And again, you would, following the similar reasoning, you would have to move the student from school 4 to school 3. So you would get this long chain of movements, those 3 movements, just because one student dropped out or opted out to go to a different place. And in some sense, it seems a bit annoying that you have to do all those 3 movements just because one person left the system. So a question that is not normal to ask is how could we have prevented this long movement? How could we have assigned people better in the first round of assignment? Yeah, first round. So a natural response to this would be to do something like inflate the capacity. So do something like overbooking, things like airlines do, for example. So you can imagine what will happen in the following scenario. Let's say we inflate the capacity at school 1, so the true capacity will still be equal to 1, or we inflate it to 2. So what that means is that we actually assign 2 people at school 1, in preparation for potentially one of them opting out for a different option. And then what happens is that the third ranked student will go to school 2, and the fourth student will go to school 3. However, because we have really no control over the opt-out stage, what might happen is that maybe all students want to keep their assignment. And so in that case, because the first school has only 1 slot, and if they are forced to move people downwards, they will have to move the second student downward. But that will actually cause the second school to be overcrowded. So what will happen is that you're going to have this long chain of movement in the reverse order. So people will be moved 1 seat downward. So again, this is something that is very unpleasant for the system. So either we're moving people upward, too many people upward, or moving too many people downward, and the unpleasant outcomes. So that begs the question, which is the central question about paper: how do we optimally overbook in a setting with priorities? So you have those priorities or those rankings of the students or of the schools, and because you have to respect them in the reassignment stage, this might lead to those long chains of movements. And the question is, how do you optimally overbook at those schools to avoid that? So some related literature to our work is the yield management literature. This goes very important for our work. The bullwhip effect literature, I'm going to be talking later about how this is relevant. And also the school assignment literature, as you can imagine, this project started from as having school assignment as an application, and that similar to our applications. So first I'm going to present the model formally, and then I'm going to be talking about an economic insight that we have that's related to the bullwhip effect. Third, I'm going to be talking about an algorithmic insight, which is a way to optimally overbook for our model. And fourth, I'm going to be discussing about a case study. We work with the San Francisco Unified School District, and we help them redesign their middle school overbooking policy. Yeah, so first, I'm going to be talking about the model. We assume that there's n items. So in our previous case, n was equal to 4. There were 4 schools. Whenever I see items, you can usually think that they're replaced by schools. So whenever I see items, you can also think about schools. And each item k has some called a q case, and it has some sort of true capacities. In our previous example, this was equal to 1 for all the 4 items. And then we have a bunch of agents. And in this, we first start with idealized model. We assume that there's perfectly aligned preferences about the items. So each agent is the same, has the same preference list about the items. And we also assume that there's perfectly aligned priorities of items. So every item or every school ranks the students in the same way. So you have this sort of like perfect ranking on both sides. Now this is an assumption that doesn't hold in the real world, but we found a way to adapt this when we work with the San Francisco Unified School District. So stay tuned for that. And another modeling assumption that helps with tractability, because I both assumptions with that, is that in the opt-out stage, each agent drops have independent probability P. So they don't really communicate with each other. They just decide make their own mind independently. So the goal is to minimize the total expected reassignment cost after opt-out. But I did tell you about what happened with the long chain movements, but I didn't actually define the cost. So the cost can come from 2 places. We have something called the underage cost. So when a student is move upward, so each time a student is moved upward by 1, we incur some underage cost. That depends. For generality in our paper, we see that it depends on which item is moved up to. And there's also an overage cost. Each time a student gets downgraded in 1 seat, that also depends on where that happens, at which item or which school that happens. And so our decision variable that we're trying to optimize for is those adjustment capacities. So basically, how much do we overbook at school? This is the decision variable that we're trying to optimize. So it's like having like an n-dimensional optimization problem. You know, the n is like the number of items, and we're trying to figure out how to optimize this objective. And we also make the assumption that overage costs are higher than the average costs, which obviously happen in a single school choice. So you would be way more upset if you got kicked out of a school that you really wanted, and you know, if you had to do some paperwork, some extra paperwork to enroll into a better school, of course. So to tie this back to our model, in the first example that we showed, we actually have a chain of underage movement, underage cost. And you can think of this as the administrative cost of learning a new student. Maybe you have to do this paperwork, maybe you have to have the parents, maybe you have to spend more time on this process. Yeah. And so the overage cost is obviously usually the loss of goodwill from downloading an agent. And you'll be very upset if you got something less good than your initial assignment. And so to give a better sense for what the cost function looks like, I wrote on the slide what the cost would look like for 1 item. This is a very similar cost function to the newsletter setting. So for those of you in the audience who are familiar with the newsletter problem, the main difference is that this binomial distribution depends on the decision variable Q1 hat, so how much we overbook a school. However, if you want to optimize just for 1 item, so if you assume that you just have 1 item, it's much capacity and want to optimize for that in our model, you will get a very similar result as in the newsletter setting. You will get something that depends on critical ratio. I have written it here because it will take too long to show that. And for multiple items, I'm not going to tell you what the cost function looks like. It's more complicated, but I'm going to tell you that the cost of item K depends on all the adjusted capacities at items that are more popular. So you can see in this diagram that the school N is influenced by all the other schools before it. So everything that happens at schools before it influences school N. For school 2, it's only influenced by its own decision of school 1, and then school 1. What happens there? What happens there only matters. Only depends on what school 1 decides. So you have this kind of like this arrow showing the influence. And so therefore, the optimal capacity at some school depends on what the other schools have said. What the other schools have said as the capacity, and what the more popular schools have done. So now we're talking about an economic insight for this model that we looked at. So the intuition is the following. So recall that the cost of item K depends on what happens with more popular items. And so in some sense, I'm not going to prove to you exactly why, but the yield uncertainty at item K can be modeled as the compound uncertainty at a single item where you bundle up together the first K items as if they were alone in their own system. So if you just remove the whole like system notion and you have the first K scores like being in their own universe in some sense, to figure out what the uncertainty would be at score K in this system that we form priorities, you would sum up the uncertainties for what would happen if they were all isolated in their own cities. So what that tells you is that less popular items have higher yield uncertainty. So there's this kind of an effect where the uncertainty bottoms up as you go further down the ranking of the scores. And this is something that happens in the supply chain management literature. It's known as the bullwhip effect, and this is why the slide has this title. Basically, what happens in supply chains is that the supplier always has way more uncertainty than the manufacturer or the wholesaler or the retailer and so on. And that's because the customer has a bit of uncertainty on what they decide, and then they pass it on to the retailer. The retailer has some uncertainty of its own, but it passes like that uncertainty and the customer's uncertainty to the wholesaler, and so it propagates up the supply chain. And so the supplier, the one who produces the raw materials, has the most uncertainty. So given that we have established that lower scores have higher yield uncertainty, how does that affect optimal overbooking and cost? So what happens there? So the first insight that we have is that at cost minimizing capacity, so at the optimal decision for overbooking, what happens is that the ratio between how much you overbook divided by what your true capacity is approximately increasing in K. What that tells you is that a less popular school generally overbook more proportion to the true capacity. Now, this is the result of obtained theoretically, and this approximately increasing is not exactly a strict increasing, but from our synthetic simulations, we see that this is actually increasing most of the time when you set some capacities, some true capacities at the scores. And the second insight that we have is about the costs. So if you assume that each school has the same associated overage and underage cost, which is most of the time a given assumption, then at the cost minimizing capacities, the costs are increasing as the schools get less popular. Now, theoretically, this is like approximately increasing, that is ratio of 1 plus epsilon divided by 1 minus epsilon, but in practice, this epsilon is very small, so this fraction is very, very close to 1. So you could replace this less than fraction times something that would like less than actually the expectation. So in general, less popular schools incur higher costs than more popular schools at the optimal capacity, and they also overbook a little more proportion to each capacity. So what those two insights tell us together is that inflating capacity uniformly, if you were to do that, actually causes a cost blow with less popular items. So in some sense, one extra motivation for finding out the optimal overbooking is not just minimizing total cost, but also making sure that there's not this cost blow at less popular schools doesn't actually exist. So now I'm going to be discussing quickly about our optimal overbooking policy. So we provide a greedy algorithm that does something very simple. So it iteratively adds a seed where it reduces cost the most. So you can think that the greedy algorithm looks to compute how much you reduce the cost by adding one seed at its core. And it looks where the impact is the greatest. It adds one seed there. And when that is no longer possible, it stops when there's no possible cost improvement. So you can think, as an engineer, there's something very greedy. It looks where it can make the most impact on the decision variable by not changing it too much, by changing just one component by one. So the theorem that we have is that we're able to prove that this greedy algorithm finds the optimal capacities that minimize total expected cost, provided that is a ratio of unit overage divided by unit underage is weakly increasing in the index of the school, which is something that is satisfied in the settings that we considered, and it's something that also the San Francisco School District said that it's an assumption that is satisfied. And the second theorem that we have that we're able to prove theoretically is this thing that is interesting from a game theory perspective. So you can imagine that each school maybe has some sort of autonomy over how much they overbook their capacity. So what will happen is that if you give the such autonomy, and we recommended the beauty solution. There, we approved that this is an approximate national equilibrium. So this beauty solution both optimizes for total cost and also doesn't give too much incentive for schools to deviate from this. So now we're going to be going over our application. So we helped San Francisco School Unified District to redesign the middle school assignment system. This consists of 3,400 students, about 70 programs in 20 schools. The preferences are made from families writing the programs. They don't have to be the same as in our assumption. The priorities are made by certain aspects, such as there's a city and a school, the students from certain neighborhood is a certain lottery number. The opt-out is pretty high, within 15 and 20% of the students go to private schools in the end. And then the previous capacity inflation was applied in a more ad hoc conservative way. So between 2 to 6% at the less popular schools, almost and basically nothing at the more popular schools. And so we tested our beauty heuristic on this model, and we found that indeed the bullwhip effect, this inequality between lower rank schools and higher rank schools because of cost, is here to stay. So even in our video evidence, this still holds as the theoretical results I showed. However, when we compared the historical capacities, we saw that this contrast between what higher rank schools and lower rank schools incur because of cost is even more stark, and also the total cost is bigger. So in some sense, this gives us the intuition that this kind of inequality between lower rank schools and higher rank schools is inherent to the descending with priorities. So we have to specify priorities. But optimizing more and more and getting close to the optimal solution actually reduces the inequality. And the outcome was that the San Francisco district changed their policy. They went somewhere in the middle between what they were doing before and what we recommended. And yeah, out of time. And yeah, thank you for listening and listening questions.
We have time for one quick question.
Thank you for the nice talk. I have a couple of quick questions. I'll hopefully clarify. So the cost is paid by the student or by the schools. I'm unclear who is being carrying the cost.
Yeah, that's a great question. So you can think of them from both perspectives. Most of our work is thought of from the perspective of the school system. So when there's an overage cost, the school system loses reputation, right? People start mistrusting the system, or and when there's an underage cost, I guess the schools also have to do some paperwork to enroll a new student. So yeah, for most of this, yeah.
But the importance is a bit unclear is that I see from a student perspective that they don't want to go to a lower tier school.
Yeah.
But from a school's perspective, they would welcome a student who would have not been able to get if there was no kind of bumping downward, right? So in some sense, I feel like the relation would be switched if you think about like the cost being incurred by students and not by the school, not the students.
Okay, so that's a great question. So the thing is that when there's empty seats, like this always provides an incentive for students to want to move forward. So what we see happening in practice is that even though previously they weren't inflating as much at the lower rank schools, there will still be many empty seats at the end because there will be a bunch of empty seats at the beginning. So people will still move out of the school. So this effect is, yeah, it's pretty
Because then part of it is the empty slots from the school's perspective.
Yeah, and yeah.
Thank you.